All right, so last time I just went over the syllabus and you started reading through the vector review and working on some problems, and I'll assign the next ones coming up. So today we're going to get into material for the class. I want to start out with just sort of I'm going to draw this kind of outline of how all the classes in mechanics fit together so you sort of can get a picture of where you're going. So I started this right. So mechanics. So this is the topic that's dealing with objects with mass and forces and accelerations and that kind of stuff. And it starts with physics 1. That's like your intro to mechanics. And then from there, it doesn't always have to go in this order, but for most people, physics 1 then is followed by statics. And then from there, you can go two directions. One direction is towards answering the question sort of like, will the object break, and what can you say about how it's going to break, that kind of thing. The other direction you can go from statics is, how will it move? As far as answering the questions about fracture and deformation and damage, the next class after statics is this one, deform. Almost every place in the world calls it mechanics of materials, but we call it deform. And then from there, you can, after deform, if you continue on this path, you can go in the direction of people who really like math, like doing proofs and that kind of stuff, or you can go in the direction of very applied, a very practical approach. The mathy direction is continuum mechanics. And then after continuum mechanics, you take more continuum mechanics and more and more and more, and it just gets mathier and mathier, partial differential equations all over the place. But no companies tend to hire people to do hand calculations of continuum mechanics. So for practical, complicated applications of the kind of things we're going to do in this class, people use finite element analysis, which is a computer approach where instead of doing the math of continuous bodies, you break up the body into a lot of little pieces and then do kind of the simple calculations on the little pieces and let the computer fit all those simple calculations together, make all the boundaries match up. So finite element analysis, you sometimes hear it called FEA for finite element analysis or FEM for finite element method. And then on the other side of this thing, you go to dynamics. And the dynamics, this is the dynamics that a lot, probably half this class is in dynamics right now. So this is the one that's based on Newton's laws. And then from there, you can go to more dynamics. And usually the second class you take in dynamics will be based on energy approaches. And then the other way you can go from dynamics is fluid dynamics. And people in different departments and with different concentrations in their departments will take different, different ones of these. If you're in mechanical engineering, you're probably, I think you take deform, but then after that you go dynamics, fluid dynamics, and then focus quite a bit more on fluids for the most part. If you're in civil engineering, most people in civil engineering, especially like structural engineering, don't have much use for like dynamics and stuff. So there's more focus on the, how do we know whether it's going to bend, going to break, that kind of thing. Anyone have any questions about any of that? I just thought that was interesting, but I was wrong. Well, what I did, by the way, thanks for asking, is I did continuum mechanics and then more continuum mechanics and more continuum mechanics. I got this job, this cushy job, this high roller. Yeah, now I'm a high roller. So I think you could say yes. Okay, so now, before we get into deform stuff, I want to go through the mathematical preliminaries for this class, stuff that maybe you've seen before, but it's going to be almost all the math we do in this class. And this is matrix math. Okay, so a matrix, usually people denote, matrix variables are given as capital letters that are either bold or, if you're handwriting it, people do the little undersquiggle. You can think of that as like the matrix equivalent of the arrow over the top of a vector. And so let's say I'm just going to make up this matrix. So 2, 1, -2, 4, 0, -6. Okay, let's say that's the matrix. So the way you describe this matrix is it's the number of rows by the number of columns. That's the size of the matrix. So this is a 3 by 2 matrix. And then to describe the individual elements, you use what people usually do is if the matrix name is capital, the element names are that letter lowercase. So, and then you represent the position in the matrix by the row number and then the column number. So like, for example, element 1, 1 is 2. Element 1, 2 is 1. Element 2, 1 is -2. 2, 2 is 4. 3, 1 is 0. And 3, 2 is -6. So you can have all sorts of sizes of matrix. You could have a 50 by 64 matrix or whatever. And using this approach, you know how to represent, how to talk about the individual elements. We're going to use 4 different matrix sizes in this class. The first one is 3 by 1. So that's something that has 3 rows of elements, but only 1 column. And so that's the way we're going to represent vectors in 3 dimensions. Okay. And we'll use this to represent directional, like unit vectors that represent directions. We'll use them for forces. We'll use them for moments. So for example, this could be a force vector, 10,000, negative 15,000, negative 5,000 in newtons. So you're used to that one. These other ones, I don't think you've probably seen yet, or at least not much. The next type we're going to see is a 6 by 1. And this is going to be what's called the Voidform of stress or strain. So like the Voigt stress, you represent with an epsilon. I'll put a subscript V so you know it's a Voigt stress. This is, sorry, strain, Voigt strain. And strain is a measure of deformation. We're talking about, you know, engineering materials, concrete, steel, that kind of stuff for the most part. I mean, you can use this for a few different things, but it has to be very small deformations for the approaches we're going to use. And, you know, steel, like if you put a load on steel that isn't going to damage it, you can't even see the deformation in it, although it does deform. And so these values are always going to be really small. So, you know, the kind of sizes we would see would be like 1.5 times 10 to the minus 5. And I just have 2 zeros. I don't know why I'm looking at my paper like I can't just make up numbers in my head. Negative 6 times 10 to the minus 6. 1, 2, 3, 4, 5, 6. Yep. Yeah. Yeah, so the only one that I don't use a squiggly line for is for vectors. This is not, doesn't have the mathematical properties of a vector. Yeah, it's interesting. What a vector really is mathematically is it's a measured quantity where if you apply a rotation matrix to it, you get the quantity that you would measure if the coordinate system was different. Okay, so like, say we have a coordinate system in this room this way. Okay, that's the coordinate system, and we take this measurement. Okay, and then we just multiply it by a rotation matrix. We'll talk about what those are later, but you multiply it to a rotation matrix. You get values that would match the values you would get if your coordinate system to start with was like this, and you took those measurements. So a column matrix isn't necessarily a vector. That's a very special thing to have that rotation matrix property. And we'll see that, you know, I'm about pretty soon to introduce tensors. And a tensor is like a 2-dimensional version of that. So a tensor is like a 3 by 3 matrix, but it's also something that you measure, and by applying rotation matrices to it, you can get the values you would have measured in a different coordinate system. So there's matrices and column matrices, and in very special cases, the matrix can be a tensor and the column matrix can be a vector. You don't ever have to remember that again. The third one, we'll see 3 by 3 matrices. And there'll be 2 times that we'll use this. One is the stress tensor. And the other one is a rotation matrix. So a stress tensor, we'll use the Greek letter sigma with an undersquiggle. And this represents the load in a body at a point. So if you are applying big enough forces to a big chunk of steel that you care about those forces, these values are going to be really big. And so these values would be like 6 times 10 to the 6, 0, negative 8 times 10 to the 7, 0, 5 times 10 to the 7, negative 2 times 10 to the 6, negative 8 times 10 to the 7, negative 2 times 10 to the 6, and negative 5 times 10 to the 7. Okay, well, if you think of, so set this aside. That's its own thing, and we'll talk about those 3 values. But notice that there's some kind of symmetry across that diagonal. This is equal to that. This is equal to that. And this is equal to that. Okay. That's not just by chance. Stress tensors have to be symmetric matrices in this way. It's called symmetric. I'll get that in your notes in a second. And symmetric matrices have some properties that are really useful. And then the last one that we'll use a lot, and this is, by the way, the main reason why you need to have this stuff programmed into your calculator or you're going to go crazy, is we're going to use a 6 by 6 matrix. That's called the Stiffness Matrix. Or, by the way, the inverse of this matrix. Have you guys heard of inverse matrices before? Some, all? I mean, I'll talk about that a little when it comes up, but the inverse of the stiffness matrix is called the compliance matrix. Oh, will you do one thing on your, I forgot to put units on this stress tensor in number 3. Just make that pascals. That's SI units for stress. The strain that I showed up above, this Voigt strain, that's already correct. Strain doesn't have any units, but stress is units of pressure. Okay, so this stiffness matrix. All right, so think about this for a second. Steel. Think about steel. Would you think of that as very stiff or very compliant? Very stiff. So the stiffness matrix, the values in the stiffness matrix for steel are very big, and the values in the compliance matrix are very small. Okay. For the stiffness matrix for the materials we're going to deal with, in SI units, it'll be like something times 10 to the 11th power. The compliance matrix will be, you know, the reciprocal of that. So that's, and so that's already, you have like your first sanity check in this class, if you ever measure a stiffness matrix and you have values that are near or less than 1, something went wrong. If you ever have a compliance matrix with values near or greater than 1, something went wrong. Okay. And I'll give you the form of this actually. So the variable that represents it is a capital E. And I'm going to show you the form of this matrix. Most of the values are zeros for the stiffness matrix. But the first element is 1 over the variable E. That E is not a matrix, so that doesn't have a squiggle. And then the second one is negative Greek letter nu over E. And the third is just like the second. And then 3 zeros. And for the second and third row, you're just moving the 1 over E, one element over each time. So the second row is going to start negative nu over E, then 1 over E, then negative nu over E, then 0, 0, 0. And then the third one is negative nu over E, negative nu over E, 1 over E, 0, 0, 0. And what is it? It sort of looks like a scripty V, like a V. And now in the fourth row, we start out with 3 zeros. And then the fourth element is 2 times the quantity 1 plus nu over E. And then 0, 0. And now for the last 2 rows, this just moves over to the right 1 time each row. So now 0, 0, 0, 0. 2 times the quantity 1 plus nu over E, 0. And then all zeros except the last element. Okay, so that's a 6 by 6 matrix. And what this is remember Hooke's law in physics 1, where the deformation of a spring is equal to the spring constant times the, well, I guess I have it sort of, so the way you do it in physics 1 is you say the force applied by a spring, you could think of it as the internal load in the spring, is equal to the spring constant times the deformation, right? And if you wanted to rearrange it, do we want to do that? No, we want it just like that. So we are going to see that the force or the loading in an object, that's the stress, okay? And actually it'll be the Voidform of the stress, is equal to this stiffness matrix times the Voidform of the strain. So you can think of this crazy 6 by 6 matrix as like a 3D version of the spring constant, okay? If the thing is really stiff, it's hard to deform it. These values are big, okay? The strain is a way to measure deformation, and the stress is a way to measure load. And so it's the same idea, but obviously the math gets more cumbersome. That's a V for Voight, yeah. And the other thing to notice about this is this stiffness matrix represents a material. Okay, so let's say you're dealing with a certain mix, a certain alloy of steel. Okay. So you'd have a stiffness matrix that represents that steel. And there are potentially 36 values in this stiffness matrix. And so in the worst possible case, you'd have to do 36 tests on a piece of steel to figure out how to fill in these 36 values. And it's not even super clear, like, it's not like it just jumps right out at you what those tests would be, you know, to mathematically be able to multiply this to the strain to get the stress, right? Well, it turns out that for very common cases, the relationship is surprisingly simple. Look at all these values. There are only two different parameters that go into filling out this entire matrix. One is E, and that's the stiffness of the material. And one is the Greek letter nu, which tells you something about when you push down on a material, how much do the sides bulge out? Or if you stretch it, how much do they suck in? And those are two easy parameters to measure. And just by measuring those two parameters, you can fill out this whole 6x6 matrix. It's sort of like a miracle, you know? Well, it only works under certain conditions, but engineering materials, these conditions are often met. And so I'm going to try to stress I'm not introducing this really mathematically yet. It's just like sort of a first glimpse at it. But when we start talking about this mathematically, I'll talk carefully about what are the sort of underlying assumptions that we need to use all these tools. There are materials where the matrix doesn't look like this. There are materials where you have 36 non-zero values, but most of the time you can make some reasonable assumptions that'll let you simplify it quite a bit. Okay. Yeah. So I'm not going to talk about matrix multiplication yet. First, let me talk about how to enter this stuff in your calculator, because you'll see when we talk about how to multiply matrices, it's very tedious to do by hand, but all of your calculators, you just use the times function if you have the matrices entered, and it does it all for you. So there are 4 ways to enter matrices in TI calculators. And if you don't have a TI calculator, we can figure it out. I'm sure it's very similar. So the first one, so which calculators use this? I think it's the TI-83 and the 84 and the 86, I think. There's a button that says matrix. So you enter the matrix button, and then you go to edit. And then from there, it lets you fill out the matrix in a very clear visual way. You know, it's a little time consuming, but it's the most, kind of the most intuitive of all of these. The second way to do it that I think works for 84s, and I think works for 86s, but not 83s, and I know it works for 89s, is to go square bracket to represent the start of the matrix, and then square brackets for each row of the matrix. So like 2, 1, square bracket, then start a new row, 2, I guess I have this as -2, 4, bracket, and then the third row is 0, 6. Oh, and this The reason I chose these numbers is because this is the matrix that I started with. So if you wanted to enter that matrix that I gave at the start of today, this is how you would enter it. And once you enter it and hit enter, it'll put it up on the screen in front of you so you can visually see if it came out the way you meant it to. The third one only works for 89s, but it saves you a few keystrokes. You just go, so you can choose whichever one of these you like if you have an 89, but you just use one square bracket for the matrix itself, and then you go semicolons to separate the rows. So 2, 1, semicolon, -2, 4, semicolon, 0, 6, end. And then the last one is for the inspire. This one, there's a matrix button, and you just fill it out as like, you just scroll around and fill out the different values. So that one, if you find the matrix, if you get to the matrix, then it's easy. It's possible that it's in a menu or something. I don't remember exactly. How many people have inspires? One. Okay. What's the other one? Okay. Okay. You'll be set for sure. It's good insurance against battery failure during exams too. I have an Inspire in my office. I'm not really used to it, but little by little, I'm sort of learning it. So we can definitely figure out how to use that. I mean, I'm sure that once you get used to it, it's the quickest of all of them. But I know that for my first few times looking at it, there's a little bit of a learning curve. Okay, so now what are the kind of things that some operations that you can do that we're going to need to do. The first one is transpose. And the way you do a transpose of a matrix is for every I and J, the ijth element of your new matrix is the jith element of your old matrix. The effect of that is you're changing rows to columns and columns to rows. You're in a way, you're kind of just dropping it over on its side, but I remember you asking, but I don't remember the context. What was that in dynamics? Oh, indeterminates. Okay, well, yeah, I'm trying to think. So now that you say it, I don't know. And I could have gone back to my office after you asked that question and looked it up, but I did not. Okay, so switch rows for columns. There's an N in columns. Okay, so for example, if you have this matrix A that's 1, 2, 3, 4, 5, 6, then A transpose is the first row is now the first column. The second row is now the second column. And the third row is now the third column. And so notice you're always switching the dimensions too. You're changing the shape of the matrix. So notice transpose takes an M by N matrix and changes it to an N by M matrix. Most TI calculators have a built-in transpose function, so you don't have to program this or anything. But it's easy to program because of actually the way you program it is this formula, basically. So come talk to me if you have a calculator that you can't find this function t when you look in the catalog of functions. Most TI calculators it looks like a little t. And in the 89, yeah, you have to go to catalog and then scroll down to t. I know some people have, and it sort of makes sense. And actually, you can do an inverse, like to do an inverse matrix, you can take your matrix and use the exponent and do an exponent to the power of -1, and it'll convert the inverse. So you might think like, I'm going to try that with this. You take your matrix, raise it to a power, and then put the letter t in the power, but it doesn't work. You have to go to that function transpose. They were. Oh yeah, between the transpose. So that makes sense to me. Is that? But you were asking like when you write it out in that. Oh, but so we were talking about the cross product.
Well, I know for like a vector with like 3x1 vector, some people do it vertically, some people do it horizontally.
Yeah. I don't either. I don't either. Yeah, usually. So, but we in dynamics we were doing cross products, and it was like, what if you take that vector and you put it sideways instead because you normally write it sideways? What happens? I don't know. Okay, the next thing that we have to talk about is square matrices. Well, that's if you weren't allowed to have dinner until you correctly guessed what a square matrix was, you would probably come up with the right, the right definition. It just means you have the same number of rows as columns. And so for example, this is a square matrix, 1, 2, 3, 4, 5, 6, 7, 8, 9. And like I did before, we can make a big deal out of that set of diagonal values. That is called the main diagonal. Diagonal values are the ones where I is equal to j. Okay. When you're talking about the element values, the element, these three elements are the 1, 1 element, the 2, 2 element, and the 3, 3 element. Okay. The other things are just called the off-diagonal elements. And those are all the ones where I is not equal to j. And it's going to turn out with the matrices that we deal with, there are fundamental differences between the diagonal elements and the off-diagonal elements. So we're going to, we'll interpret these in different ways. So this is true of all square matrices. There's also an important special case. So a special kind of square matrix. And that is a symmetric matrix. You can't have a symmetric matrix without it being square, but you can have a square matrix that's not symmetric. And the requirement is that the matrix itself is equal to its transpose. In other words, the ijth element is equal to the jith element for every I and j. So an example of this, I gave an example earlier, but let's say 1, 3, -1. Well, this 3 is the 1, 2 element. That means that the 2, 1 element also has to be 3. The diagonals they can be whatever they want. And then let's say this is 4. Okay, well, the next one is the 3, 1 element. So that has to be the same value as the 1, 3. So what value does this have to have? Yep, -1. The next one is the 3, 2. So that has to be the same value as the 2, 3. So what number does this have to be? -4. And then this can be anything. So it's symmetric because after you forget about the diagonal, the 1, 2 equals the 2, 1. The 1, 3 equals the 3, 1. And the 2, 3 equals the 3, 2. Yes, the stress tensor matrix is a symmetric matrix. Yes, it has to be. You don't have to remember that yet. We'll talk about that when we talk about the meaning of a stress tensor. But yeah. So here are some things to keep in mind about symmetric matrices. Well, it's only 2 things, but both of these are important. The first one is that a symmetric 3x3 matrix a 3x3 matrix obviously has 9 values, but a symmetric 3x3 matrix only has 6 independent values. Say once you choose the values in the upper triangle, that fully determines the values in the lower triangle. So only has 6 independent values. And because of that, we can always write a 3x3, a symmetric 3x3 matrix in Voidform. And Voidform looks like this. So if you have a matrix, let's call it A11, A12, A13, and let's say it's symmetric, so I'm going to call this also, even though this is the 2-1 element, I'm going to call that A12, A22, A23. And this one, because of symmetry, is A13. This is A23. This is A33. The Voidform is first the 3 diagonals in exactly the order you would expect. And then the 3 off diagonals in exactly the opposite order you would expect. Why they do that, I don't know. But so what would make sense for the next element? Obviously 1, 2, right? So nope, that's going to be last. And what would you do next? 1, 3. Nope, that's going to be second. And what would you do last? 2, 3. Nope, that's going to be first. So this is the Voidform. And I don't know where that order comes from. It's odd, but that's just how it is. Okay, so that's the first. I'm almost done. That's the first important fact about symmetric 3x3 matrices. And the second one is all eigenvalues of a symmetric matrix are real. In general, eigenvalues can be imaginary. But if the matrix is symmetric, the eigenvalues are real. And what that means is that in any application where your eigenvalue means something physical that has to be a real number, like say your eigenvalue is a measure of force or something like that, then it has to be coming from a symmetric matrix, because if it's not symmetric, you know that you could get eigenvalues that are complex, and you can't have complex forces, that kind of thing. So this fact that the eigenvalues are real is going to be useful to us. We're going to use the eigenvalues of tensors, of stress tensors. Okay, I have a couple more things to say, but I'll do that on Friday. So, all right, see you Friday.